when you change something's potential energy, it is the opposite of the work done by the field. Now, this part's hard, and some of you aren't going to get it, and I'm okay with it. It sounds like it's just a minus sign. It's more than that. Because when we do gravity in mechanics, I need you 26 people to be like the experts on how to deal with electric potentials and gravitational potentials. It's hard to appreciate the difference, but this minus sign means a lot, and they play with it quite a bit on the exam. So there's a difference between an external agent doing work and the work done by a field. We would say that in the same example as yesterday, so I want to get right back to this idea of a uniform electric field. And is 3 field lines good enough to say it's uniform? Or must I draw like 5? 3 will be good, right? Oh, good. Thank the maker. There. So this is my uniform electric field. If I just plop a charge right here, if it's a positive charge, it automatically experiences a force to the left. And that force would be equal to QE. This is the force on the charge from the electric field. If I move it from here to here, the field can't make it go that way. There's no way for the field to do that. We talked yesterday about the fact that when it gets over here, does it have more energy or less energy? And what kind of energy would it have? It will have more potential energy. Sure, and the amount of potential energy will be QED as long as this distance is D. Now, at the same time, the particle just can't get over there. If I want to move the particle over there, I physically have to push it. This would be an applied force. Something external to the system would have to push on the particle and move it against the field. Now, this force, by definition, would have to do positive work. It fits all of the criteria for positive work. I'm pushing it in the direction the particle goes. So force used to move a particle. That is the technical definition of work done by an applied force. So it has to be positive. And we know that the amount of work done would have to be exactly the same as QED, but would be positive. So we can say, with a little hand waving, that work done by an applied force is negative the work done by the field, which is also stored as a change in potential energy. I want you to have this concept in hand frequently. Right now, it's pretty straightforward. But we can't actually move charges like this. In a circuit, we almost always are dealing with an unknown number of charges. And in a circuit, we don't move charges one at a time by applying a force. We use wires and batteries and other things to move charges around. But that doesn't change the fact that in a circuit, we're going to build up charge to create electric fields. And those electric fields therefore store energy, and this forms the basis for how we calculate that energy. The problem is that we never know how much charge there is, or we never easily know how much charge there is. So just like when we define the concept of the electric field based on how much force there is on a particle that isn't there, remember our concept of the test charge? The idea that we find out the force on a particle and then divide away the value of the charge. That was where the concept of the electric field came from. We're going to develop the electric field doesn't provide a zero. A uniform electric field, because it is by definition uniform, doesn't have a place where there is no energy unless you go out to the infinite. So generally a picture like this wouldn't provide a location where there is a zero potential. In order to understand this, we're going to talk about a more complex problem. I want to talk about building a group of charges together and calculate the amount of energy associated with that group of charges. The things we're going to derive today, you will reuse for every potential problem. This is like Coulomb's law for potentials. So you'll use this over and over and over again. You'll use it for groups of charges. You're going to use it for a charge distribution. There is no Gauss's law for potential. So this is the only way to calculate potential. I want to start with the simplest idea I can, and that is the placement of a single point charge in space. How much work does it take to get that first charge there? Zero. If I want to place another charge in the space near the first, I have to do work on the charge to get it to this location, a distance r away from the first charge. To calculate the work from the field in moving that charge, I'm talking about calculating the integral. Now my ending location is going to be a distance r away. Where do you think my initial location has to be in order to find a place where there's no energy between the two charges? How many of you would agree infinity makes reasonable sense here? I need to go infinitely far away from the first charge. That's right. When we draft the concept of a potential, the electric potential is relative to a position of infinity. This is how you calculate an absolute potential. You have to start at a place where there's absolute zero for energy. Yes, ma'am?
I don't have my glasses. Is infinity at the bottom?
Yes.
Of it? Okay. And then at the top is R. Okay. Thank you.
Well, I kind of like watching the people in the back. Oh, by the way, I'm getting a new projector. I found out I can order one with my AP money. So here's what we're going to do. We're going to talk about how to do this, but before I get into it too much, we're going to change this a little bit, because the truth is you would never do it this way. We have defined the electric potential to be the work done divided by the charge. In this case, we're talking about the work done by the field divided by the charge. That would suggest 1 over q times the integral from infinity to r of f dot dr. But f is defined as QE. That's the definition of electric field. It's the force divided by the charge. Which means the actual calculation for electric potential from now on is going to be E dot dr from infinity to r. But remember, I put work done by the applied force earlier, and I changed it to work done by the field here. So I have to put an explicit negative sign in here to account for that. This is the definition of electric potential that I want you to know and I want you to use. It's on your equation sheet. It's the definition of electric potential. The explicit negative sign is very important here. I spent a period talking about where it came from. potential difference is similar. We just rewrite it to deal with two places in space. So electric potential, we take the potential from a point infinity. The potential difference is the difference just between 2 points. Be careful. For what they give you in a problem often is important in this discussion. So if they ask for a potential difference, they're suggesting there's a starting place. You need to take that into account. Now, just a brief aside, this is the dot product, don't forget it. The direction's important. However, also don't throw away the meanings here. This delta does not mean differential. Okay, it doesn't mean differential. Potential difference is an absolute path-independent difference. That's why it's a delta. I'll say that again. The potential difference is path-independent. It's a true delta. So don't think that this represents the differential. It does not. I'm saying that because if I strip away the integral, here, I can, dot product. I would write this as the derivative form before the integral. We won't use this very much. In fact, maybe not at all. However, I mean, you can find the electric field from this, because the electric field has got to be the derivative of the potential with respect to position, not time, with respect to position. This has to be true. The problem is, to get from here to here, I had to wave my arms and throw away the dot product. Did you notice that? I just made it disappear. I didn't talk about the cosine or anything. That's because this way of finding the electric field can't tell you the direction of the electric field, just the size of the electric field. You would have to use something else to figure out its direction. But everybody who's finished calc knows that finding a derivative is easier than finding the integral. Because of that, this might become your go-to way of finding the electric field. Is find the potential first and then take its derivative, as opposed to setting up a complicated electric field calculation and taking the integral. I told you we would find easier ways to do almost everything. So going back to this discussion with Q right here, and I'm bringing a charge from infinity to a place right here, a distance r away. I want to talk about how to calculate this electric potential. That potential will be minus the integral from infinity to r of E dot dr. You hear that, right? Maybe it's a dentist working on somebody right now. I want you to consider this point for just a moment. This point is experiencing an electric field right here, this place in space. So we're trying to go from infinity to this location at space. If I stop at this location for just a moment and consider this place, this intermediate place between infinity and a distance r away, the electric field there would be Q over 4 pi epsilon naught, and let's call this R2 squared, where this is R2. This is the size of the electric field at this location in space. And that electric field would be pointed away from charged capital Q. I'm bringing it up because I need to find a way of writing the electric field from this charge. Since it's a point charge, I just write it like this. So when I go to find my electric potential, Sounds like a Dremel tool. I can write it like this. The problem is that, and I should erase this a little bit, I need to be cognizant of direction of everything. So I'm trying to be very careful here. So I put my R hat to remind me that the direction of this field is pointed away from the charge, dr. And it's in the R hat direction, the direction of R. But I want to move it this way, even though the field points that way. I'm trying to move it from infinity closer to the charge, which suggests that a Dremel tool, a weed eater. I'm not even sure where it is. They're not on this roof yet. It's always something, isn't it? And you guys know that I'm a little neurotic about it, so I can't just turn it off. And I'm trying to focus here. Because I have to take the dot product into account, I need to make sure you know that I'm going towards this particle, but there's a cosine 180 here that I also have to take into account. So when I calculate the electric potential, I'm going to have this -1 here, and I have this explicit negative sign out front. So before I've even done the integral, I'm going to have to cancel out those two negative signs. Now, I know that this is hard to follow, and my little interludes with the grinding machine are not helping. But at this point, we're setting up this integral and trying to calculate the electric potential at this point in space. Right now, I've got the integral from infinity to r of q over 4 pi epsilon naught r squared dr. Remember, this part is just the electric field from a point charge. This is the integrating variable required because we're just calculating work done. And we're going from very far away to something relatively close. Got all those pieces together? So there's not a whole lot here. I'm trying to go slow, but I think I'm just sounding like I'm halting and not really slow. Because now we have to actually do the integral, and this is where a lot of you have difficulty. But I do want to point out that q, 4 pi, and epsilon are all constants in this equation. So all I'm really doing is the integral of 1 over r squared to dr. And this one is actually really easy to do. So to take this integral, just a reminder that we're finding the antiderivative of r to the -2 power. To find this antiderivative, I add 1 to the exponent, and I divide by the new exponent. And this is my antiderivative. Everybody okay with that? Any questions about that? We're good to go? All right. So, q over 4 pi epsilon naught times -1 over r evaluated from infinity to r. This will be the electric potential. So V is q over 4 pi epsilon naught I'll have 1 over r minus 1 over infinity. And there's a negative here. It's out front. I just pulled this negative out. So, what we get, and because the bell rang, I need to just summarize before we walk away. And I'll talk about where that negative sign disappeared to in just a minute. There was something else we had to do. But this represents the electric potential near a point charge. And by extension, if I have a distribution of charge, this must represent the electric potential from a piece of it. Just like with Coulomb's law. What I want you to understand here and note and take significant notice of, it's very similar to the electric field, except it's over r instead of r squared, but with no directional component. It's a simple sum. We're going to redo a bunch of these like bent pieces of charge and figure out what their electric potentials are, but they're so much easier because there's no direction involved. Every part contributes based on how far away it is, and that's it. And you're going to like what we do tomorrow. It's super easy. Reminder of where we got to yesterday. The electric potential and this is the absolute potential, is equal to Q over 4 pi epsilon naught times R. It's the electric potential. Now, I want to be very careful about this. This is the electric potential in the space surrounding a single point charge. So if I have a point charge Q, the electric potential here, a distance r away, is given by this relationship. Now, there's several important implications here, and I'm trying to be slow and deliberate because otherwise I'll speed off and go in some tangent. I don't want to do that. Since the definition of electric potential is the amount of energy per unit charge, you can find the amount of potential energy when you know the electric potential for a point charge placed at that location. So at this moment, there are Q over 4 pi epsilon r volts of electric potential at point P. When I put charge Q here, the amount of energy in this system would now be Q over 4 pi epsilon naught times R. This would be the amount of electric potential energy in the system. So if I were to hold capital Q in place, like lock this one in so it couldn't move, and release the charge at point P, it would eventually have a kinetic energy equal to QQ 4 pi epsilon naught R. So after this spirits away, I could convert all of that potential energy into kinetic. And moreover, you could even figure out how fast the particle's going. All of these are kinds of things you can figure out by knowing the electric potential. That idea transitions even to another situation, the one we talked about originally. imagine having two charged plates. One positively charged, one negatively charged. Negatively charged with an electric potential difference V between them. If I were to carefully, I gotta do this just right. If I were to carefully drill a hole through one of the plates, then if I dropped positive charged particles here, I could tune this device to shoot charged particles out the hole. They wouldn't all make it, but anytime one was lined up perfect to make it out of the hole, I'd get a particle that would come out of the hole, a beam of particles. This area has a electric potential that's based on the potential energy we calculated the other day, QED, suggesting that the potential difference between two plates is just E times D. But this would also suggest particles exiting the hole would have a kinetic energy equal to QED. So that's how much potential energy each particle has when dropped there. When they move across the potential difference, that's the amount of energy they acquire as in the form of kinetic energy. This is a simple particle accelerator. Particle accelerators are used in everyday tasks. In fact, old televisions used a particle accelerator on electrons to create the picture on the tube. Even old school plasma displays use small particle accelerators to create the photons of light that we saw. Simple particle accelerators are made in this way. This device with the two plates creates a nice uniform electric field. And as you can kind of imagine here, that potential energy could also be written Q delta V. So we could, by knowing the voltage, determine how fast the particles are traveling. Batteries are marked with voltages. Supplies are marked with the voltage they supply. Measuring voltage is super easy. So you could physically tune your device to provide just the right velocity if you wanted. I mean, solving this for the velocity gives you a way of tuning your device to make sure particles come out of the device with very specific velocities. No discussion of electric field. I don't even have to know how far apart the plates are, which is why you could make this really small if you wanted. It's all just based on the potential difference. So you can probably imagine that I envision a whole group of particle-based questions. Questions that ask you to do simple conservation of energy calculations to determine what potential might be necessary for a certain velocity, or how fast would a particle have to be going in order to make it a certain distance away from a charge. All of these kinds of questions are the kinds of simple, straightforward point charge problems that you would expect to hear. We're going to talk about 2 or 3 of them, okay? Here's the first one. If I have a single proton located in space that is fixed in space, how fast would another proton launched from infinity have to be traveling to make it 2 femtometers away? I'll say the problem again so you get accustomed to hearing some of the terms. But I have a single proton that is fixed in space. How fast would another proton need to be fired so that it could approach the first and reach a distance 2 femtometers away? Just so you guys know, getting into the femtometer range is what it takes to get inside the nucleus of an atom. This calculation is a real calculation. This is what's occurring in the sun in order to fuse hydrogen into helium. So this gives you an idea of how fast the particles are traveling in the sun. There's no way around this. So when they talk about knowing how fast atoms are traveling in the sun, they can measure it based on the brightness of the sun because they know how much energy must be in that particular sun. And these materials that are there are all readily available on the Earth and measured. This is how you figure out how fast the particles are moving. Therefore, it tells us our temperature. Remember I said from the beginning, particle velocity is directly proportional to temperature. So let's work this problem. This problem begins with the understanding that electric potential for any point charge, bless you, is Q over 4 pi epsilon naught times R. The amount of energy required to get the particle to this location is going to be Q squared over 4 pi epsilon naught, where R is 2 femtometers. Is there any question about where I came up with that? Yeah.
Where did the Q squared come from?
Well, first, potential energy is Q times the potential. They're both protons, so they have the same charge, so this becomes capital Q times the potential to indicate it's the same charge as the fixed particle. And then I just drop this in for electric potential. Am I good? Now, if I want to figure out how fast, so here we go. Once I know how much potential energy has to be in the particle when it makes it to this point, I know how much kinetic energy it had to have had when it was launched to make it there. These kinds of ideas that the particle started from infinity but is going to move to this point is really just going way back to last year's discussions of how do you deal with conservation of energy. The electric force is a conservative force, so it conserves energy. So the amount of kinetic energy here will have to equal the amount of potential energy when it finally comes to rest at this point. So for me to figure out how fast it was fired, I need to equate the kinetic energy with the potential energy. It's not a big deal, but until you've kind of seen these a couple times, it can be tough. In this case, 1/2 mPv squared. Mass of the proton, I want to make sure I understand that I'm firing a proton, has to equal Q squared over 4 pi epsilon naught R. And that's how you figure out what the velocity is. Now, we don't need to do the calculation, but I think you should. And here's why. The mass of the proton is 1.67 times 10 to the negative 26 kilograms. Epsilon naught, you should already know, 8.85 times 10 to the negative 12 meter squared per Newton Coulomb squared. Pi, you guys know, but Q is the elementary charge of 1.6 times 10 to the negative 16th coulombs. I want to see you mash those numbers together. And 2 femtometers is 2 times 10 to the negative 15th meters. Now, do you see why I want you to do this? It's much less about can you put a couple of numbers in and find V. It's can you deal with this? I mean, yeah, there's no way of even knowing before you start what to expect for this velocity. It could be anything. So give it a shot. I bet 25 people in the room, 26 people in the room, I bet we get about 12 different answers. That's my guess. Particle physics or radiation physics, this is how they determine the amount of energy that was in the nucleus prior to it being separated. They use that to help calculate the binding energy of the atom. Binding energy isn't a hard calculation, but figuring out why the helium got kicked out isn't necessarily something that's straightforward. As I indicated before, it's supposed to be covered by something called the weak nuclear force. We don't really know what does that. We know that some of the particles over on this side interacted with some of the particles over on this side, and that's what kicked out this particle. But we don't know why helium is what gets kicked out, not an individual proton. We don't really understand the mechanics of that. But you probably do see then that there's going to be MV for plutonium and MV for the helium, and they have to sum to be 0. They don't receive equal amounts of energy, though. And you can see why that's probably true. So in this case, you would have to deal with the fact that you get an energy equation and a momentum equation with 2 unknowns, V for helium and V for plutonium. At the same time, we know how much energy was there beforehand because we know how many protons are here and how far apart they all are. And we can use that to effectively determine how much energy existed before. Generally, we just take the helium and treat it as one particle and the plutonium treat it as another and say that they started 2 femtometers apart and calculate how much energy must have been there. So for plutonium, that's 90 protons, and for helium, that's 2 protons. So our Q1 would be 2 times the elementary charge for helium, and Q2 would be 90 times the elementary charge for plutonium. And this is a real thing. This also tells you why you get radiation burns near an alpha emitter. You're actually physically burned by the particles striking your skin and you having to absorb that kinetic energy. So when they talk about radiation burns, if you guys, anybody watch of assembly questions out there, we're going to see these quite a bit in the literature. They exist a lot in the multiple choice. They'll ask how much energy would it take to assemble this system if I have 4 charges of value Q arranged on a square of side length S. This is one of the more common styles of question. And it doesn't have to be a square. In fact, it doesn't have to be this at all. It could be 4Q, negative 3Q, 2Q, and negative 7Q. In each case, this problem is the same whether it looks like I just drew or looks like that. The calculation isn't as hard as it sounds, except I want you to consider what it takes to do this calculation. How much energy does it take to put the first charge there? 0. So I don't have to calculate the energy to say put this one here. So if that's the first charge, no big. To bring the second charge up in place, then I have to calculate how much energy there is between this one and this one, because this one was here first. To bring the third charge in place, well, there's already 2 there before. So I have to calculate the energy between this one and this one and this one and this one. If I want to bring the last charge in place, well, you kind of see what's going on here, right? Assembling a group of charges will therefore have energy based on what it takes to bring each charge into position. Now, this is not the typical question. This question occurs once in a while. The most typical question, though, isn't what I just described. But I think we could do that problem. And to do it, I'm going to draw all these arrows, mostly so you understand that you're going to be adding together 6 different energies, right? 1, 2, 3, 4, 5, and 6. Now it's all straight adding. That's the part that's great. So like energy number 1, that's going to be Q squared over 4 pi epsilon naught times S. Let your mind wrap around it a minute, but does everybody understand why that's the amount of energy for number 1? Any question about where I came up with it? So energy number 2, 3, and 4 are all the same amount, right? They're all the same charge, all the same distance away. So there are 4 of those. Direction doesn't matter. Any question about what I just did? Well, let's look at number 6 for a minute. Q squared again over 4 pi epsilon naught times, well, this distance is the square root of 2 times S. Right? It's the diagonal of a square. You could do Pythagorean theorem, but you might just want to start putting together that's always going to be square root of 2 times that value. And how many of those are there? So that's the answer. You can make it look nicer, but this is the answer. So although, yeah, I had to add together 6 things, there's a lot of symmetry in the problem. If I was to write this out, I'd probably write Q squared over 4 pi epsilon naught on the outside and have 4 plus 2 over the root of 2, which is, my understanding, just the root of 2. Questions about that? Now, just in closing, the most common question ever asked isn't that at all. It's easier. The most common question asked is to find the potential at a single point, like at one of the charges or at the center. That is the most common question, which again is just a straight addition of potentials. Of the electric potential. To be based on the amount of work done divided by how much charge was done, how much charge was used to do that work. We're going to call this the electric potential. We use a capital V for it. Again, we're going to talk about how much work was done to move a charge, but then divide out by the amount of charge that's there. Generally, we talk about the amount of work done by the applied force in this instance. And this is also therefore written as the change in potential energy per unit charge. Now, just before we go on, this is going to be joules per coulomb. And in deference to Alexander Volta, we call this the volt. Sometimes we'll talk about voltage. This is the building block for energy in the circuit. We don't talk about energy straight. We talk about energy per unit charge. Now, there's a couple of nuances in here that I want you to pay attention to. Delta U is the change in potential energy between two configurations of charge. We talked about that at the very beginning yesterday. So delta V is called the potential difference. Batteries don't provide an electric potential. Batteries provide a potential difference. This is why there's a negative side of the battery and a positive side of the battery. The terminals of the battery are so constructed as to create a potential difference. They provide reference for where the start of the potential is and where the end of the potential is. This is why multiple batteries can be used together. So if you stack batteries, which is what's happening in your calculators, what's happening in your flashlights, when you stack batteries, you are increasing the potential difference across their terminal. Potential differences add together. More importantly, potentials and potential differences are scalar quantities. So because of that, simple addition and simple rules of mathematics govern them. More importantly, because they're not vectors, they have no direction. We don't have to take direction into account when dealing with potentials. So potentials are positive, potentials can be negative. You can have an instance where we take potential away in the same way that we do negative work. But the beautiful thing about this is that potentials are scalar quantities. The best thing about it is we can get the electric field from the potential, which suggests that we can deal with a scalar and then add the vector part of a problem later. This has amazing advantages. It's going to take some of the work we've done and make it much easier, because finding the potential is easier than finding the electric field. However, we do have to consider the possibility of what the difference is between a potential difference and the straight electric potential. See, a battery provides a potential difference because it doesn't actually provide what we consider to be an absolute zero. The electric potential is a potential difference where one of the potentials, this one, is a place of no energy. When we calculate the electric potential, we are actually calculating a potential relative to a condition in which there was no energy before. A place of zero potential. We generally don't have easy access to places like that. There's always charged particles around us, and therefore we are always surrounded by potentials. Most things that we're going to ever deal with, especially in circuits, they're only going to be potential differences, even though we tend to call them the potential or the electric potential. In most cases, they are nothing more than a potential difference. And that means that the negative side is establishing the low point of the potential. And the positive side is establishing the high point of the potential. And therefore, there is a difference between the two terminals. But a straight electric potential means we're talking about a point relative to a zero in space. A